Hi, today we're going to talk about determinants and permutations, which is section 1.4 in the Professor Thomas notes. Okay, and we already saw that the determinant came up in the characteristic polynomial, right? We said that if A is an n by n matrix, then the determinant, this characteristic polynomial, the determinant of A minus ti, is a polynomial of degree n in t. And we even said that this was equal to negative 1 to the n times the product of t minus each of the eigenvalues, as long as you allow for complex eigenvalues. Okay, so today we're going to try to understand exactly what the determinant is in a little deeper way than in Math 308. Okay, so first of all, let me introduce some notation, which many of you have seen before. If n is an integer, if n is a natural number, then I'm going to define n factorial is like this. You notate it with an exclamation point, and it's just the product of all of the natural numbers up till n. Okay, so that's what n factorial is. A permutation of the numbers 1 through n is just an ordering of the numbers. Okay, so for example, if we let n equal 2, then how many permutations are there of the numbers 1 and 2? There are 2. There's 2 possible orderings, right? If n equals 2, then there are 2 permutations of 1, 2, namely 1, 2, and 2, 1. Okay, and we, by convention, will not write commas in between the numbers in a permutation. We're only ever going to write out like actual permutations for small sets. We would never try to write out all permutations on 10 numbers, say, because that would be a huge number. And so in practice, this isn't going to be confusing. Okay, well, how many permutations are there of 1, 2, 3? So if n equals 3, how many permutations? Well, we can try to write them down, right? So there's 1, 2, 3. There's 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. And this is all the possible permutations of 3. I've written down the numbers 1 through 3 in every possible order. And so there are 6 of them, and it's not an accident that there are 3 factorial of them. Okay, so 2 is also 2 factorial. Okay, why are there 3 factorial permutations of the numbers 1 through 3? Well, you can just think, if you write down what a permutation is, it's just an ordering of the 3 numbers. You have 3 choices for the first number. It could start 1, 2, or 3. And then for the second number, you have 2 choices, right? If you picked 1, then the second number is either 2 or 3. If you picked 2, the second number is either 1 or 3. If you pick 3, the second number is either 1 or 2, right? So you only have 2 choices for the second one. And then once you've chosen the first and the second one, the last one is forced, and so you only have 1 choice for the last thing. And so these 6 permutations here is every choice of the first one paired with every choice of the second one, and then the third one had to come along for the right. Okay, so similarly, there are 24, which is 4 factorial permutations of the numbers 1 through 4. I don't need the dot dot dots, of course. Okay, so one way that you can think of a permutation is as an ordering of the numbers 1 through n. Okay, there's another very useful way to think about it, though. So another perspective is you can think of a permutation of n as a function. I'm going to call it pi from 1 to up through n to itself. Okay, that actually has to be 1 to 1 and onto. Okay, well, how do I think of a permutation as a function? Okay, so let's write down some example permutations of the numbers 1 through 4, right? So I could write down the permutation, I don't know, 1, 4, 3, 2. This is one possible permutation. Here's another one, 2, 1, 3, 4. Here's another one, 3, 2, 4, 1, right? These are all permutations of 1 through 4. And what I can think of the function, or to each of these permutations, I can assign a function. What the function does is each digit in the permutation tells you what the function does to the next number. Okay, so this thing I can think of as the function that sends 1 to 1 because 1 is in the first slot. It sends 2 to 4 because 4 is in the second slot. It sends 3 to 3, and it sends 4 to 2. Right, and because on the left-hand side, I've written every number exactly once, therefore the function that I come up with will be onto. It will hit every single number in the set. Okay, so to each permutation, I can associate a function. And also to every one-to-one and onto function, I can associate a permutation just by looking at where 1 goes, then where 2 goes, then where 3 goes, then where 4 goes. Okay, so similarly, this permutation here I can think of as a function that sends 1 to 2, it sends 2 to 1, it sends 3 to 3, and it sends 4 to 4. And this permutation here I can think of as a function that sends 1 to 3, 2 to 2, 3 to 4, and 4 to 1. Okay, another way to write this, by the way, is if I call this function pi, then what I mean is pi of 1 is 1, pi of 2 is 4, pi of 3 is 3, pi of 4 is 2. Okay, so I'm not going to call these bottom ones pi because once you've used a name for a function, you shouldn't reuse it. Okay, and one last thing, which the notes mentioned, is here I said the permutations of 1, 2, 3 up to n. Another way to say this, just for short, is I'll just say permutation of n. So another way to say that is that these are all permutations of 4. Okay, this is just shorthand, so I don't have to keep on saying 1, 2, 3 up through n. Okay, now it turns out that I'm not just spouting off about permutations for no reason. There's a very close connection between permutations of n and the determinant of an n by n matrix. Okay, so let's consider the determinant of a 3 by 3 matrix and of a 2 by 2 matrix and try to understand what the relationship is with permutations. Okay, so let's do the 3 by 3 example. So what a generic 3 by 3 matrix looks like is it looks like this: A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, and here I'm sticking to the normal convention where the first number denotes the row, the second number denotes the column. Right, so this element here is called A12 because it's in the first row and the second column. Okay, now you learned in 308 how to compute the determinant of a matrix. By a cofactor expansion, what you do is you pick any row and any column and you do a cofactor expansion along it. So let me just cofactor expand along the first row just so we can all see it. The determinant of A, what does a cofactor expansion do? You take each element in that row. So we start with A11. Then you ignore the row and the column. So you ignore this row and you ignore this row. You ignore this row and this column, and you take the determinant of the remaining piece. So times the determinant of A22, A23, A32, A33. That's the first term in the determinant. Then you take minus the next element in the row, A12. And again, what you do is you ignore this row and you ignore this column. You take the determinant of what remains. Determinant of A21, A23, A31, A33. And then similarly, you take plus A13, determinant of A21, A22, A31, A32. Okay, and now these are 2 by 2 matrices, so we can write out what their determinants are. A22, A33 minus A23, A32 minus A12 times A21, A33 minus A31, A23 plus A13 times A21, A32 minus A22, A31. Okay, and then we can expand, and let me be careful when I'm expanding and make sure I'll write them in an order where the row index goes 1, 2, 3, right? Because I can commute these numbers past one another. So A11, A22, A33, that's the first term, minus A11, A23, A32. That's the second term. Here I have minus A12, A21, A33. And then the next term is plus A12, but let me write the A23 first so that the row, if you look at the row numbers, it goes 1, 2, 3. Of course, numbers are commutative, so that's fine. And then plus A13, A21, A32, minus A13, A22, A31. Okay, now this thing looks a bit like a mess. Okay, if I told you to tell me what the determinant of this matrix is, it would be probably at this stage hard for you to remember this formula, right? This is not a formula that you memorize. What you memorized was the process by which you computed the determinant. Okay, but if we look at the terms appearing here, we can maybe gain some insight. Okay, so first of all, if I treat the aij's as variables, then note that this polynomial is a polynomial in the aij's of degree 3. Right, so every term here is a product of 3 variables. Okay, not only that, but there's 6 terms. And each term is either plus 1 times the product of variables or minus 1 times the product of variables. Each term is plus 1 times some product of variables or minus 1 times some product of variables. And instead of calling this a product of variables, let me call this a monomial in the aij's, right? So it's either plus 1 times a monomial or it's minus 1 times a monomial. Okay, so now let's look closely at each of the monomials, okay? What I'm gonna do is I'm gonna zoom in here so I can point a little bit better. So the first monomial there, A11, A22, A33. If you look at the indices, right? If you look at these indices, notice that in the first index, 1, 2, and 3 each appear, and in the second index, 1, 2, and 3 each appear. That means that in this monomial, we have 1 variable from each row, and we have 1 variable from each column. Okay, but the same thing is true of all the other monomials. If you look at this monomial, we have 1, 2, and 3 appearing in the first index, 1, 2, and 3 appearing in the second index. If you look at the third monomial, we have 1, 2, and 3 appearing in the first index. We have 1, 2, and 3 appearing in the second index. Okay, so each monomial consists of 3 variables, and each of the variables, each row is represented once, and each column is represented once in each monomial. The monomial consists of 1 variable from each column and 1 variable from each row. Okay, but then I said, well, I'm going to arrange them so that if we look at the first index, it always goes 1, 2, 3. I can do that, right? Because I can always commute these aij's past one another. And notice that if you just pay attention to the second index, you see 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. What's happening in the second index? What's happening in the second index is we're getting exactly this list of permutations. In fact, even in the same order. So there's some relationship between the determinant of this matrix and permutations of 1, 2, 3. Right? Because somehow every permutation here is present exactly once, embedded in a monomial of this type, with a plus or a minus sign out front. Okay, so let me grab this and move on to the next slide. I actually don't love all these little arrows that I drew, but I'll erase them. Okay, so there's our nice determinant of A. And as I said, if you pay attention to just this, the first index is always going 1, 2, 3, and if you pay attention to just the second index, you get the permutation 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And they occur with some sign, right? Plus, minus, minus, plus, plus, minus. Now, it turns out that we can understand these signs that are appearing in terms of the permutation as well. Okay, so here's the definition. I'll say that a pair ij is inverted. Oops. Sorry. Is inverted in a permutation pi if I is less than j, but pi of I is greater than pi of j. So in other words, you call a pair inverted if the permutation changes their order. Okay, so let's go back to this list of permutations here. So in this first permutation, 1, 4, 3, 2, which pairs are inverted? Well, 3, 4 is inverted. Let me do this in different color to sort of show that it came later on in the lecture. So which are inverted? Three, 4 are inverted because 3 is less than 4, but pi of 3 is greater than pi of 4. Okay, also 2, 4 is an inverted pair because 2 is less than 4, but pi of 4 is 2 and pi of 2 is 4, so pi of 4 is less than pi of 2. Is anything else inverted? Yes, 2, 3 is also inverted because 2 is less than 3, right? 2 is less than 3, but if you look at where pi of 2 is 4 and pi of 3 is 3, so pi of 2 is greater than pi of 3. Okay, so an inverted pair is one where after you do the permutation, the one that's bigger switches, right? So I would say that this permutation has 3 inverted pairs. right? Because 1 isn't inverted with anything because 1 went to 1. 2 is inverted with both 3 and 4. 3 is inverted with 4. Okay, so that's what I mean by the by an inverted pair in a permutation. Okay, and then we say that a permutation is even if it has an even number of inverted pairs and we say that it's odd if it has an odd number of inverted pairs. Okay, so a permutation, which is just an ordering of the numbers, or you can interpret as a function from the set to itself. You can either call it even if it has an even number of inverted pairs, or odd if it has an odd number of inverted pairs. And then third definition, the sign of a permutation is 1 if it has an even number of inverted pairs, or if the permutation is even, in other words, and -1 if the permutation is odd. If the permutation. In other words, it's -1 to the evenness or oddness of the permutation. Okay, so now let's consider the determinant that I have at the top of the page, whether these permutations are even or odd. Okay, so in fact, let me drag this bit down so I have some room to write underneath this determinant. Okay, so this permutation, how many inverted pairs does it have? Well, it doesn't have any inverted pairs because this permutation sends 1 to 1, 2 to 2, and 3 to 3. So if I is less than j, then pi of I is less than pi of j, because pi of I is just I and pi of j is just j. So this one has 0 inverted pairs, which means that it's even. And so the way that I can write this is I can say the sign of 1, 2, 3 is 1. The sign of the permutation just tells you whether it's even or odd. Okay, what about this one? How many inverted pairs does this one have? Well, 1 is not inverted with anything because pi of 1 is 1. But 2 and 3 have been inverted here. 2 is less than 3, but pi of 2 is greater than pi of 3. So this one has 1 inverted pair. 2, 3 is inverted. So this is an odd permutation. In other words, the sign of 1, 3, 2 is -1. Okay, let's continue with the rest of these. How many inverted pairs do we have here? Here, 1 and 2 are inverted. Also, 2 and 3 are inverted. No, sorry, just 1 and 2 are inverted. 1 and 3 are not inverted because they appear in the correct order. 2 and 3 are not inverted because they appear in the correct order. Right, so the way that you can detect an inverted pair is by seeing which pairs of numbers appear in the wrong order in this expression 2, 1, 3. And there's only one pair that appears in the wrong order, 1, 2. So this is also odd, so it has sign -1. Okay, what about this one? 1 and 2 appear in the wrong order, and 1 and 3 appear in the wrong order. So 1, 2, and 1, 3 are both inverted. In other words, it's even, and so its sign is +1. This permutation, 1 and 2 are not inverted. 1 and 3 are inverted. 2 and 3 are inverted. So it's even, and it has sign +1. And then this last one, 1 and 2 are inverted. 1 and 3 are inverted. And 2 and 3 are inverted. So this is an odd permutation and has sign -1. Okay, and hopefully what you noticed is that this sign exactly matches the sign that it appears in the determinant. Right? In other words, it looks like we should be able to write the formula for the determinant, where for each permutation you get a term. It's going to be a product of n monomials with a sign that comes from the sign of the permutation, either plus or minus 1, depending on how many inverted pairs that permutation has. That's what it looks like we can do. If that's true, though, it better be true for 2x2 matrices too, which luckily are easier to understand. So let's think about whether our formula makes sense for the 2x2 matrix case. So here's the 2x2 example. Hopefully we all know that it's easy to write down the determinant of a 2x2 matrix. It's exactly just A11, A22 minus A12, A21. Okay, so I've written them so that the first index increases, goes 1, then 2. So if I were to understand which permutation this one was the permutation 1, 2. This one was the permutation 2, 1. There are only 2 permutations of 2. What about the signs? Well, this one has no inverted pairs, the first one. So the sign here is 1. This one has a single inverted pair. 1, 2 is inverted, so the sign is -1. And that is exactly the sign that's appearing as a coefficient for these terms. So the formula seems to work for the 2x2 case too. Okay, and in fact, you can prove that this formula works in general. We're not going to spend... The proof is basically just a bunch of really horrible note keeping with the indices. I'm going to state the theorem, and hopefully, because we've seen this full example, we can understand that theorem. So if A is an n by n matrix, by the way, this notation here just means that the ijth term of A is Aij. In other words, this is just shorthand. This is just shorthand for this matrix when n equals 2, and for this matrix when n equals 3. It's just you take the matrix that has Aij in the ijth slot. Okay, so if A is an n by n matrix like this, then the formula for the determinant of A is like this. Okay, so first of all, it's a sum of n factorial terms, right? So we have one term for every permutation. That's what happened in both of these cases. So it's a sum over all pi, where pi is a permutation of n. So I'll have one term for every permutation. It's going to have a plus or minus 1 out front that depends on what the permutation is. And then each term is a product of n monomials, right? So this one was a product of 2 monomials. This one was a product of 2 monomials. For the n equals 3 case, we had a product of 3 monomials. And what is the product? You have one, let me leave blank the second index here. You have one term for every row. And then the second term, that's just given by the permutation. So A1 pi of 1, A2 pi of 2, A3 pi of 3, up through an pi of n. If you do this for every possible permutation, that will give you all of the terms, and they appear with the sign that's just the sign of the permutation. Okay, and it turns out that understanding the determinant in this way can genuinely be very useful, because now you understand, it's not just a whole mess of terms that you don't understand. It's a whole mess of terms that you understand very deeply. You get one for each permutation. The indices, the permutation tells you exactly how the indices behave in each term, and the sign that appears out front is just the sign of the permutation. Okay, so this formula will also help us understand the characteristic polynomial of a matrix. Okay, so we may come back to this formula at various points during the class, but now think about the characteristic polynomial. Okay, so let's again take A to be the 3 by 3 matrix, A11, A33, right? Just the normal 3x3 matrix. What is the characteristic polynomial? The characteristic polynomial was determinant of A minus Ti, which means that you took the matrix and you subtracted T from each of the diagonal entries. So let me now be very careful and write out the entire matrix. Okay, now, what is the determinant? It's going to be a sum of a bunch of terms. Okay? Now, which of the terms will have a t in them? Well, the terms that have a t in them will be exactly the ones that use any of the things along the diagonal. Right? And it turns out that, well, there's only one term that will have a power of t cubed in it. That's the one that corresponds to the permutation 1, 2, 3, right? So it's going to be a sum of stuff. Let me just write stuff here. But if you look at the permutation 1, 2, 3, you'll get a term that's just the product of these things. In other words, this will be negative t cubed plus some other stuff. And that's the only term in the determinant, that's the only term amongst the stuff that can possibly have a t cubed in it. Because no other term involves a11, a22, a33. In fact, it's even the only term that will even have a t squared in it. Because if you picked two of these, then you would be forced to have the third one. Right? If you pick a11 and you pick a22, the only term that's left is a33. So every other term, so maybe let's say it like this, this is going to be equal to this plus stuff of t degree less than or equal to 1. So the only time a t cubed or even a t squared appears is in this term corresponding to the permutation 1, 2, 3. In other words, this is guaranteed to be the t cubed term of our determinant, which shows that the determinant is going to have degree exactly 3. Right? So this shows that the degree of this determinant, of this p of t, is equal to 3, and that the sign in front is negative 1. That's the coefficient on the t cubed term. And then you should think about which parts of this argument, hint, basically all the parts of this argument, work for n bigger than 3. Turns out for any n by n matrix, if you think about what the determinant is, only one of the terms will contribute a t to the n. It will be exactly the term that takes all of the things along the diagonal. All the rest of the terms won't even involve a t to the n minus 1. They involve at most t to the n minus 2. Wait, is that true? No, that's not true. Is that true? No, it is true. It is true. If you picked n minus 1 of the terms on the diagonal, you'd be forced to take the last term on the diagonal as well. So every term, the highest degree term comes from the diagonal. So you have t to the power n. And you'll have either an even number or an odd number of them. It will occur with a minus 1 to the n term. And so this argument shows that the characteristic polynomial will be a degree n polynomial in t, where the monomial out in front is negative 1 to the n. That's going to be true in general for any characteristic polynomial. Okay, so that's what I wanted to cover today. This is a bit shorter than the lectures on Monday and Wednesday this week. I think that's okay though, because last lecture I really wanted to make sure that you had the logic primer even before you turned in your first homework. Not that the first homework was pretty computational, but I wanted to get that early. And the first lecture was really just review. And I guess I made you watch the syllabus video before classes started. So let's just end here today. Next week, we're going to talk about lots of fun stuff. We'll start talking about difference equations. We will talk about Markov chains, and then we'll talk about Google PageRank at the end of the week. So we finished chapter 1 in the notes of Professor Thomas and Sam Rovin, and we're going to continue on this schedule that they've set from the winter quarter. All right, see you next week.